All right, we are going to look at Taylor polynomials. We've kind of already done this before whenever we found the equation of a tangent line, and then we use that tangent line to approximate the function values. We're going to do almost the same thing, except instead of a tangent line, we're going to find a polynomial of degree n, whatever that might be, that has that same function value at that point. It also has the same slope, the same concavity, the same third derivative, the same whatever derivative that we want. So essentially, the idea is we're taking a function and we want to write it as a polynomial instead of just how the function is. And that polynomial, kind of like how that red line approximates the blue graph, is going to essentially approximate a function that we're given. If we really think about this and work it out by hand, we'll see some of this in class, you're going to get the following formula. So degree n, wherever n is either given to you or you get to choose, and the value of c, we call this thing the center of our Taylor polynomial. Think of that like our point of tangency, where those things meet, with a tangent line. That's going to be a function value that we're starting with. And at that point, on that y value of our graph, we're going to have the same derivative. So f prime of c, same concavity, f double prime of c. And depending on the order, or I'm sorry, the degree, which is either given to us or we choose in any given problem, that'll tell us how many derivatives that we have to take. Also, if the point in common, or that center, is 0, we actually call this a Maclaurin polynomial. So let's see graphically how this is going to work out. So let's take a look at a GeoGebra animation here that works very nice by Doug Kuhlman. I believe I used his on some other videos. So here I have the function. Oh, come on, let me. Okay, I guess I'll just have to I guess I'll just have to zoom in. So I have this function f of x equals sine of x, and it's centered at 0. So I'm actually looking at Maclaurin polynomials. Here I have a polynomial of degree 1, so that makes sense that it's going to be a line. If I look at a third degree polynomial, it's going to be that nice cubic graph that looks like it's going to match our graph even better. So then here's our formula, x minus x cubed over 3 factorial. And if I look at, say, the 5th degree and the 7th and the 9th, looks like each degree I go up, I have more derivatives, and my polynomial looks closer and closer to our graph. That's essentially the idea. So let's actually work a quick example here. Let's say that I'm trying to approximate e to the x with a third degree polynomial centered at x equals 12. So first I want to find my derivatives. Okay, that was pretty easy. I only need 3 because it's a third degree polynomial. I also need the derivative values at x equals 12. I'll just plug in 12 for x. So a third degree Taylor polynomial centered at 12 would look something kind of like this. P sub 3 of x equals f of 12 plus f prime of 12, x minus 12 to the 1 over 1 factorial, plus f double prime of 12 times x minus 12 to the 2nd over 2 factorial. You can kind of see the pattern here. And if I actually plug in those derivative values, it's going to look like this. So this is going to be a third degree Taylor polynomial centered at 12, which approximates e to the x.